Good morning, everyone. My name is Sirsha Banerjee, and I will be presenting the topic of lifting flows over a cylinder. Let's get started. So, our agenda will be to discuss the how we can model the case of rotating cylinder for the fluid flow motion, as well as we will discuss on the velocity potential and the stream function. After that, we will discuss about the lift and the drag force and the Kutta-Joukowski theorem. Let's get started. Welcome everyone to this interesting discussion of the presentation of the phenomena of lifting flows around a cylinder. Now, if we look at the flight of a bird to the streamlined hull of a ship, the principle of fluid dynamics plays a very crucial role in shaping our world. At the heart of this fascinating field lies the study of how the fluid interacts with a solid object, and that particular case can be typically represented by the flow of air or water around a cylindrical body. Let's see how we can do or model that particular case. Now, if we have the non-lifting flows over a cylinder and we superimpose that particular flow with a vortex flow of strength of gamma, we can get the lifting flows over a rotating cylinder or the flow of a rotating cylinder. Now, if we look by the potential theory, the complex potential function can be given as velocity potential plus iota times of the stream function. And we know that this particular scenario of the lifting of the flow of the rotating cylinder is basically modeled by superimposing the uniform flow, the doublet flow, as well as the vortex flow of strength of gamma. And we also write a constant to incorporate for the case that the phi, when we superimpose phi 1 plus phi 2, the phi should be equal to 0 on the contour of this particular cylinder with radius, the small r or radial distance is equal to the capital R, that is the radius of the cylinder. So then we can get the phi as v infinity r sine theta multiplied with 1 minus r square by small r square plus gamma by 2 pi ln r by capital R. Now with this, if we look at the how to analyze the flow pattern of the streamlines, we can note the stagnation point. Now stagnation points are those points where the velocity is equal to 0. That is equating the radial velocity and the angular velocity is equal to 0 in the 2D notation using the polar coordinates. Okay, so if we apply Vr is equal to 1 by r del phi by del theta and v theta is equal to minus of del phi by del r, and we obtain and equating to 0, we obtain the stagnation point as radial distance is equal to r and the angular distance or the azimuthal angle is equal to sine inverse of minus gamma by 4 pi u infinity into capital R. So those are the location of the stagnation point. Now, depending on the value of gamma, we have the different streamline cases which are shown in the figure. With this, let us move and understand how we can calculate the lift and the drag force. Now, for calculating the lift and the drag force, let us consider any arbitrary body of this particular fashion in a fluid flow of an uniform with a uniform fluid flow with a velocity u infinity. Now, if we consider any elemental distance dl or an elemental section, for this particular section, if we consider the pressure acting at an angle theta with the horizontal, then we can also transpose the dl segment into dy and dx components. Now, if we look at the drag force, the small drag force is given by minus p dl cos theta, which is also equal to minus p times of dy. Now, here the minus sign signifies for the resistive force which is acting on the body for the motion of the body in the x direction. And similarly, the lift force can be calculated by the force in the vertical direction, which is equal to the pressure times the dl sine theta, which is also p dx. Now, if we observe the small force of the small drag force minus iota times of small lift force, which is equal to minus p dy minus iota times of p dx, and if we simplify this equal to minus iota times of pressure into del z conjugate of del z. Now the total force can be given by the closed surface contour integral of this particular elementary force on the elementary length of dl. Now if we perform this integration for potential flow by the Bernoulli's principle, that is P infinity plus half times of rho u infinity square is equal to the pressure at any position plus half times of rho q square, which is the velocity whole square. And if we are neglecting the gravitational term, then we can get the q square is equal to u square plus v square. Okay, and that is given by u minus iota times of v multiplied with u plus iota times of v. And if we simplify the relation, what we can see over here is that this particular expression simplifies to this particular expression. Now, the interesting case is observed is that u plus iota times of v multiplied with dz conjugate becomes equal to u minus iota times of v with dx plus iota times of dy, and this particular relation corresponds to the dz. Okay, because for the streamline, what we can observe that u dy minus v dx tends to 0, and if we look at the integral of this constant term, that is p infinity plus half times of rho u infinity is a constant, and hence its closed integral over the closed surface contour is equal to 0. Now the total force, that is a drag force minus iota times of the lift force, we can simplify to this particular relation. And after this, if we simplify from the expression of the velocity, that is u minus iota times of v, which is given by differentiating the function f with respect to z, then we obtain the relation of the force is equal to iota by 2 times the closed surface contour integral of rho times of del d, differentiating the phi, the velocity, the potential function with respect to z, and squaring it, and then we take the the closed surface integral, and this particular relation is also known as the Blasius-Closed theorem. Now, if for the cylinder or the rotating cylinder, if we obtain the differentiating the function f with respect to z, we obtain the expression something like this. And now, if we evaluate the integral by the Cauchy residue theorem, what we can observe is that Cauchy residue theorem says that the integral of the closed integral of this particular function fz over dx is equal to 2 pi iota times the sum of the residue at the points of singularities. Now, if we evaluate for the point of singularities of differentiating the f by z whole square, it is same as finding the coefficient of 1 by z. Now, this can be seen from the Lorentz series expansion. Now the coefficient comes out as 2 u infinity iota times of gamma by 2 pi, and if we put this value in the expression of the force, then we can calculate the force as minus iota times of rho u infinity into gamma, which simplifies the result for the total force, that is the drag force is equal to 0 and the lift force is equal to rho multiplied with u infinity multiplied with gamma. And that particular expression is also known as the Kutta-Joukowski theorem. That is, the force acting per unit length of a cylinder at any cross section is equal to rho multiplied with the u infinity into gamma, and it is perpendicular to the direction of the u infinity, where rho and u infinity are the fluid density and the fluid velocity for far upstream section of the cylinder, and the gamma is the circulation, which is defined as a closed line integral of the velocity over the surface. Now, with this, we can observe that the force of a cylinder can also be extended to the case of an aerofoil section, and that particular transforming the geometry of a cylinder to an aerofoil section can be done by conformal mapping, and thus the force on a aerofoil section can therefore be calculated from the force on a cylindrical section by doing this conformal mapping, which is shown over here. With this, I tried to create a simulation of the rotating cylinder motion on a CFD in ANSYS by firstly creating the geometry, then doing the meshing, and then doing the initial setup condition, and then understanding the solution in the CFD post. So I only tried to create the streamline for pattern for this flow with the specification given as the radius of the cylinder as 4.58 meters and the angular velocity is given as 50 radians per second. So the streamline is given as this. Okay. So with this, if we look at some of the interesting phenomena of this, is very interesting phenomena is the free kick by Roberto Carlos. The outswing of the free kick by Roberto Carlos is also a very phenomena of the generation of the drag force due to the differential pressure on the two different side of the rotating cylinder or rotating sphere. What we can see over here. Okay, and along with this, we can also note the interesting phenomena of the calculating the lift force, which draws its application in the hydrofoil craft as well as the aircraft. With this, I come to an end, and on concluding note, I can say that the lifting flows over a cylinder is a very interesting phenomena, and this lift is generated due to the difference in the pressure distribution of the cylinder, with low pressure on the upper surface and the high pressure on the lower surface, which therefore generating the net upward force. The lift is also generated by the flow over the cylinder is significant for various engineering applications such as aerodynamics, hydrodynamics, and the design of structures like aerofoil and marine vessels. Understanding the mechanism behind the lifting flows over a cylinder is essential for optimizing the performance and the efficiency of these particular systems. And with this, I come to an end, and thank you.